shapes aren't always as simple as triangles and squares. Sometimes they can be complicated, like this shape over here. And finding the area and length, there's no formula for that. It requires ingenuity and some problem solving to figure it out. And we're going to learn some techniques to make finding area and lengths of complex shapes much easier, like finding the area of this shape. Let's start off with hexagons. So a hexagon, we already discussed some angle chasing properties in the previous video, where the sum of the interior angles is 720, and each interior angle of a regular one is 120. The exterior angle is going to be equal to 60, and there's a key, nice little, and also the diagonal of a regular hexagon is 2 times the side length of the hexagon. The area is 6 times square root 3 over 4 sides squared. And there's a clever trick you can do to realize this. Notice how we can draw, if we draw, we can split a hexagon into 6 equilateral triangles. And then we can see the longest diagonal is just 2 times the side length of the equilateral triangle, which is also the side length of the hexagon. And the area is just 6 times the area of an equilateral triangle formula. So the key idea for regular hexagons, it's often a good idea to break it down into 6 equilateral triangles. But this is only true for regular hexagons. Hexagons with 6 equal sides and 6 equal angles. Okay, now let's try this problem. Vincent the Bug draws all the diagonals of a regular hexagon with area 720, splitting it into many pieces. So this hexagon has area 720. Find the area of the smallest piece. So this is the area of the hexagon. We're trying to find the area of the smallest piece, which you can see that it's going to be something like this piece, right? It's going one of these pieces. They're all the same. All 4 of these tiny pieces are the same. And as you can see, I've drawn all the diagonals of this hexagon. We're essentially trying to find the area of that blue shaded region over there. Okay, so this is just a random region in the middle of nowhere. How are we going to find its area? Well, here's what we're going to do. Let's say the side of a hexagon is S. Now, why are we going to say this? Because it's a regular hexagon. All sides are equal to S, and all angles are going to be equal. And remember, in a regular hexagon, each interior angle is going to be 120 degrees. So that's 120 over there. Oh, but now look, S, it's an isosceles triangle. This one is an isosceles triangle. And that means that these 2 angles are equal. So if these 2 angles, we call them x, we have 2x plus 120 equals 180, meaning that x equals 30. Because 180 minus 120, 60 divided by 2. So each of these angles over here is 30, and this angle over here is also 30. Now notice something. This over here is the exact same triangle. S, this angle over here is 120, so we get the exact same thing. By isosceles triangles, these 2 angles are both 30. So 30 and 30. So what do we do with these 30-degree angle conditions? Well, we're just trying to figure out maybe this region. Well, because this region, in order to figure out its area, it would be helpful to have some angle conditions, right? But because we don't know anything about this. We don't know its side lengths. We don't know its angle. We just know it's some random region in the middle of nowhere. Okay, so how are we going to go from here? So let's continue our angles. So this is 30, right? And notice that a hexagon is symmetric about all 6 of its sides. Oh, and it looks like I forgot to draw 2 of the diagonals. This one and this one. Sorry about that. So it seems now we can see that there's actually a bunch more of these regions, not just 4. There's a bunch of these small regions. And they're all the same because hexagon is symmetric. So they're both the same just by symmetry. And you could technically do a rigorous proof if you'd like, but this is not a proof contest, so symmetry is a good enough argument. So by symmetry, these two triangles are going to be congruent because it's a symmetric situation. And that means these two angles are equal. Let's call them both x. Aha! Now notice, the interior angle of a regular hexagon is 120. So 2x plus 2 times 30 equals 120. If we add all of the parts of this angle up, we get 120, which means 2x plus 60 is 120, or 2x is 60, x is just 30. Aha! 30. Whoops, did not mean to do that. This over here is going to be 30, and this over here is also 30 as well. Okay, my eraser's not working today. Okay, so now we've got a bunch of 30-degree angles. That's very helpful, of course. 30, 30. Notice here, S, this part is 30, and by similar logic, we can all, it's a symmetric situation, right? So we would also find that each of these parts over here is 30, 30, 30, 30, 30, right? Because it's sixfold symmetry, and in these types of situations, everything is going to be symmetric about each of its vertices. So each of these parts is also going to be 30 as well. So 30, 30, aha! That means that this over here is an isosceles triangle. Because 30, 30 means these two sides are equal. Also, let's call this angle y. Now we have 2 times 30 plus y equals 180 because of the sum of angles in a, whoops, I'm blocking. Because of the sum of angles in a triangle formula. And this gives us y equals 180 minus 60, 120. So this over here is 120. Oh, but now look, this is 120, so now supplementary angles tells us that this is 60. And if 30, 60, 30, 60, 90 triangles. 30, 60, 90. Because 30 plus 60 plus 90 is equal to 180. This angle must be 90 for the sum of the angles in this triangle to be 180. Aha! A 30, 60, 90 triangle. That is very helpful. But we still don't even know what any of its side lengths are. So how do we go from there? So let's try to find its side length in terms of s. Let's see if we can do that. S, well, so S is on the outside. We want to try to relate it to the inside of the diagram. How should we do that? S is on the outside, 30, 60, 90. Another 30, 60, 90 triangle. These things are just everywhere, aren't they? 30, 60, 90. Because 30 plus 30 is 60. And if the hypotenuse is S, the short leg is S over 2. That's neat. Okay, so we've already found one side length of this small triangle. Remember, we're trying to find the area of that small region here. We found one of its sides, but what about this one? We can use our 30, 60, 90 ratios. And so let me erase what I just did because that's going to cause clutter. Notice how in this triangle over here, the S over 2 is the length of the side opposite the 60-degree angle. So the one opposite the 30-degree angle will be S over 2 divided by root 3. It's going to be root 3 times smaller because this side is root 3 times bigger than this side by our 30, 60, 90 ratios. So now, what is the area of that blue shaded triangle? Half base height. The base is S over 2. The height is S over 2 root 3. And this simplifies to S squared in the numerator and 8 root 3 in the denominator. Well, we don't know S, but the main condition we do know is the area is 720. But we know the formula for area of a hexagon in terms of side length. So we can backtrack that and use that to find S, which we'll then plug in here. Let's do that. So the area of a hexagon, 720, is equal to, remember, we can break the hexagon into 6 equilateral triangles. Each of them has side length S, and the formula for equilateral triangle is root 3 over 4 sine squared. So for a hexagon, it's 6 times root 3 over 4 side squared, which gives us 120 is root 3 over 4 side squared. But we're looking for s squared over 8 root 3, which is, if we multiply by root 3 to the numerator and denominator, gives us s squared root 3 over 24. S squared root 3 over 24, s squared root 3 over 4. That's just going to be 6 times bigger than this, because we can rewrite the 1 over 4 as 6 over 24, which gives us, when you divide by 6 to both sides, 20 equals s squared root 3 over 24, and 20 is going to be our answer. So 20 is the area of this shaded region. So the key idea here was just drawing all the diagonals, and then noticing the symmetry. That was the key here. And then seeing that you're doing a little bit of angle chasing using isosceles triangles, finding two different 30, 60, 90 triangles. That gives us, this is s over 2 divided by root 3, and this is s over 2. And then we just find an expression in terms of s, solve for the hexagon thing in terms of s, and yeah, we're just done after that. And there's actually another way to solve, there's actually many different ways to solve this problem. There's not one for sure. But another way you can do this is notice that this side length over here is root 3 times less than this side length over here. Let's draw that. This over here is root 3 times less than the red side length over here. And the red side length over there by 30, 60, 90. So red equals root 3 times purple. I know I'm using such nice variables here. And then we would also have that green is root 3 times red. This is root 3 times this because of the 30, 60, 90 triangle as well. And this would give us that the green one is root 3 times red, which is root 3 times purple, which is 3 times purple. So that means this over here is a third of this over there. And then from there, we can see that the area of this triangle is just going to be 1/3 the area of this triangle because they have the same height, and the base of this bottom one is 1/3 the base of the big one. So height is the same, base is 3 times less. So the area of the we're looking for is 3 times less than this area. And let's call this area the purple region. The blue region is 3 times less than the purple region. And then notice that this purple region is half of an equilateral triangle. Because if two of these regions make up one equilateral triangle. So the purple region is half of an equilateral triangle, and there's 6 equilateral triangles that make up the hexagon, right? There's 6 of them. Because there's 6 sides of the hexagon. So the equilateral triangle is 1/6 of the area of the hexagon, which is 720. And that's 120. And then the purple region is half the equilateral triangle area, which is 60. And then we found out that the blue region was 1/3 of that because of they share the same height and the base is 1/3. So 1/3 the purple region, which is 20. We got the same answer using 2 different ways. Okay, now let's solve this problem over here. An equilateral triangle ABC, points P and R lie on segment AB, as you can see here. Points I and M lie on segment BC, and points E and S lie on segment CA, such that primes, this hexagon over here, is equiangular. Not regular, equiangular. Huge difference there. For a polygon to be regular, it must have 6 equal sides and 6 equal angles. For a polygon to be equilateral, it must have all of its sides equal. And for a polygon to be equiangular, it must have all of its angles equal. A regular polygon is both equilateral and equiangular. So key distinction there. Be careful about that. So equiangular hexagon, what does that mean? The total sum of angles in a hexagon is 6 minus 2 times 180 by our polygon formula, which is 4 times 180, 720. The average measure of an interior angle of the hexagon is this divided by 6, which is 120. So because it's equiangular, each angle is equal to the average of the whole polygon. Each of these angles will indeed be equal to the average angle because all the angles are equal. So all of these angles are 120. That's essentially what that means. Okay, that's not very helpful, is it? We don't know the sides are equal because it's not equilateral. It's just equiangular. Let's look at these conditions here. AB is 11, okay. So, okay, now we know the side of the equilateral triangle. TS is 2, so that's 2. RI is 3, that's 3. ME is 5, okay. I know it's not to scale, but that doesn't really matter. So the question is, how do we use these 120-degree angles? Immediately, right off the bat, 120. Notice that if this is 120, by supplementary angles, this over here will have to be 60, because 60 plus 120 is 180. Similarly, this will have to be 60, and this will have to be 60, and this will have to be 60, and these two things as well, right? By the supplementary angles. And also, we know that the triangle itself is equilateral, right? The triangle itself is equilateral, which means that all three angles of it are going to be equal to 60 degrees. So we know that right off the bat, this is 60, this is 60, this is 60. 60, 60, 60. 60, 60, 60. 60, 60, 60. Is that a coincidence or does that mean something? If a triangle has three angles that are 60 degrees, it's an equilateral triangle. Now, this is only true for triangles, by the way. For example, if a rectangle had if a quadrilateral has 490-degree angles, it could still be a rectangle. So only for triangles is it true that if the three angles are equal, then the three sides are equal as well. So the three sides are all equal. Aha! We know PS is 2, right? PS we're given is 2. But then we have that equilateral condition because the triangles, all those three-cornered triangles, they're all equilateral. That's cool. So then we would have that because this is an equilateral triangle, this part is 2, and this part is 2 as well. Now, this triangle over here is also equilateral because of the 60-degree angles. And that means all of its sides are equal as well. You can probably figure out what to do from here as well. Because Ri is 3, this is 3, and this is 3 as well. So this over here is 3, and this over here is 3. Now the reason I'm doing these things is to be clear that 3 is not like this or this. I'm being very clear, it's just this part. And similarly, because 60, 60, 60, this triangle is equilateral, so all the sides are equal. That's 5, and that's 5. So now how do we find the area of this hexagon? This hexagon, notice how it's nothing but, so there's generally two ways to find areas of complex shapes. One is to break it down into pieces that are easier to handle, like this, for example. And then you could try and find the area of these four triangles. Another way is to find the area of something bigger and subtract off what you don't need. And in this case, that's going to be much easier because we can just find the area of the large equilateral triangle and subtract off the areas of these three smaller corners. So let's do that. Now we can just use the equilateral triangle area formula. Okay, so the formula for the area of an equilateral triangle, the formula for the area of an equilateral triangle is just square root 3 over 4 times the side length squared. So the area of the inside region will just be equal to the area of the big equilateral triangle, which has area of root 3 over 4 times 11 squared, right? This whole thing, root 3 over 4 times 11 squared, minus the area of this triangle, which has area root 3 over 4, 3 squared, minus the area of this triangle, which has area root 3 over 4, 5 squared, and similarly, the area of this triangle, which is root 3 over 4, 2 squared. So this over here is the sum of these extra areas we're trying to subtract. So we subtracted it from the area of the big equilateral triangle, which is this. Now it's just a little bit of computation. 121 over root 3 over 4 minus 9 root 3 over 4 plus 25 root 3 over 4 plus 4 root 3 over 4, which is minus 9 plus 25 plus 4, that's 38 root 3 over 4. And now this is just 121 minus 38 root 3 over 4. And 121 minus 38 is 121 minus 40, 81 plus 2. So 83 root 3 over 4 is our final answer for this problem. The key idea here was noticing that equiangular means these angles are all 120, and that means these angles are all 60. And then from there, we could see that if this is 5, that's 5, that's 5. This is 3, that's 3, that's 3. 2, 2, 2. Also, by the way, another remark is that sometimes they may not give you an equilateral triangle. They'll just give you an equiangular hexagon. And in that case, the best strategy is to extend the sides to form those equilateral triangles. Remember, just because something isn't there doesn't mean you can't make it. You have all the power. You can do whatever you want. And that includes extending the diagram. So if, for example, if this part was not there, if they just gave you an equiangular hexagon, they didn't give you this part and this part, then you can just extend it out to form that equilateral triangle and use that property. That's a good trick to keep in mind. Okay, now we're going to talk about octagon. So octagon average interior angle or the angle of a regular octagon is 135. The sum is 1080, right? We're calculating this using the formulas we learned in the first video of geometry. The exterior angle is just 360 by 8, 45. And this is a formula for the area, 2 times 1 plus root 2 times s squared, or simply 2 plus 2 root 2 times s squared. Now, it can be good to know, but if you ever forget the formula or don't want to memorize it, because memorizing is not all that easy all the time, then the trick to finding the area, like I mentioned earlier, there's generally two ways to find area of complex shapes: break it up or find more and subtract. So if this is S, we would get 45, 45, 90 triangles here. So we would find that this is S over root 2, S over root 2, S. And then this over here would just be S as well. So S, 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 S over root 2, S over root 2, S over root 2, S over root 2, S over root 2. Now notice how it's just the sum of these four triangles plus 4 of these rectangles and a square on the inside. And we found these ratios using 45, 45, 90. And another way, which is probably a bit easier, is you can extend the sides of the octagon. We could extend the sides of the octagon, form this. And now what you could do is find the area of the square and subtract the four corners. And just like earlier, 45, 45, 90 gives us the side length of the square to be s root over root 2 plus this. And then you can subtract off these four triangles by just finding the area of those. Okay, yeah, these are kind of the techniques. Divide the shape into nicer areas, extend lines, right? That's always good. like we did here, extending the lines to form those corners which we subtracted from. And then also breaking up areas, right? That's also helpful sometimes, like we broke it up into these parts. And sometimes more than one way can work like that. And also sometimes it can be helpful to find the area of shapes in terms of variables, even if you don't know the exact values. And then you can use that to solve for variables. So just because you don't have the exact value, don't let that shy you from finding areas in terms of variables, like S for hexagon or something like that, right? Okay, let's try another example of this. Or, yeah, let's try one more example of this. In rectangle trig, don't worry, we're not doing trig here. We're just doing geometry. We've got a nice little rectangle called trig here, and it's just a name of the rectangle. T-R-I-G. Points A and L lie on sides TG and TR. Let's set TA, AG. So let's do here. TA is AG, meaning this is equal to this. TL is 2LR. So this part is 2x and x, something like that, right? Diagonal GR intersects segments IL and IA at B and E. Let me do something a little bit different here. I don't think I've done this before. I'm going to use dotted lines. So diagonal GR intersects segments IL. Where's IL? Okay. IL, let's use dotted lines again. IL like that. And IA at B and E respectively. So IL at B and IA at E. Suppose the area of convex pentagon with vertices table is equal to 21. So we're given this random area, convex IAE and ILB, yeah. So table, which is table here, is equal to 21. Okay, and we're asked to find what is the area of trig, which is the entire rectangle. So table is this thing here, this pentagon here. And we're asked to find that if this area is 21, find the area of the rectangle. So you know how we let this be 2x and x? Let's do something similar here. Let's let it be y and y. That's going to be easier to work with. So y and y. Okay. And this is 3x, of course. 2x plus x, right? 2x plus this part. What is the area of this entire rectagon in terms of variables? Like if you don't know what the area is directly, in terms of variables, 3x times 2y, 6xy. Okay. Now, we know this area of table is 21. So a good strategy is we know the numeric value. What if we try and find this area in terms of variables? Then we can solve for those variables and find the area of the rectangle from there by plugging it in here. So let's find the area of table. Let's find the area of the pentagon using variables instead of a numeric value. Okay, so trig. So how should we go about doing that? Notice here we've actually got a bunch of parallel lines. First of all, right? Rectangle lines are parallel. So essentially, to find the area of table, rather than breaking it up, it's probably going to be easier to find the area of this and subtract off these pieces. So the area of table and this notation over here just means area, is equal to the area of this triangle And what is the area of this triangle? Half base height. Half base is 3x, height is 2y. So 3xy. That's the area of the triangle. So the area of the entire triangle is 3xy, this triangle. Now we have to subtract the areas of this part and the area of this part. So what is the area of this part, first of all? Let's shade the blue region. I like using colors. What is the area of the blue region? Well, we know in terms of variables, of course. Well, we know the base is y, so half base. We don't know the height. Or do we know the height? Think about this for a minute. Try and figure out the height. How we can find out the height. Notice here, these two sides, they're parallel. And parallel sides come to similar triangles. Yes, we're using similar triangles again, if you remember that. Used to solve these complex shapes. So, because these lines are parallel, we would have that. Look, if you think about this like that, and this is a transversal, these two angles are going to be equal. And we also have these two angles are equal by vertical angles. So this angle, this angle, this angle, this angle, a similarity. Aha. So the blue triangle is similar to this triangle here. But what is the ratio of similarity? The base is y, and this base is 2y, so 1 to 2. We still don't know how to find this height here. How does that even help us? Similar triangles? Well, what do we know about similar triangles? What does it preserve? It not only preserves side and angle ratios, but also height ratios as well. So the ratio of the heights of these two triangles, the ratio of this height to this height, let's use a brighter color. This height over here to this height over here, the ratio of this to this is the same as the ratio of the bases. So this height, this triangle over here is 2 times bigger than this triangle here. So the sides are all 2 times bigger. So the height will be 2 times bigger as well. This will be 2h. But we don't know what h is in terms of x and y. The key thing to do here is we can see that both h and 2h combined, they make up 3x. So we have 3h, which is this total length from here to here, equals 3x. Because they both make up the length of the rectangle. So h equals x. We can erase that there, and write that as x, erase this here, write this as 2x. So the area of the blue triangle, oh, I erased the blue, is half yx. Great. So now we found the area of one of the regions we have to subtract. What about this one here? Let's call it the green triangle. Yay, green. Green triangle. The area of the green triangle. We're gonna have to do something very similar. The half base height, right? The base is x, and then the height, we don't know what it is. Let's call it, what's a good variable name? L. Because we already used h, I don't want to use that again. So that's L, and notice here, these are again parallel sides, and you can think of that like a transversal. So, because these are transversal, we have, and these two are parallel lines, by alternate interior angles, this angle is equal to that angle, right? The parallel angle chasing properties. And also we would have that these two angles are equal by vertical angles. So if these two angles are equal and these two angles are equal, then the triangles are similar by a similarity. And I'm just showing this to be completely rigorous, but you don't actually have to do that. You can just directly notice that parallel lines generally mean similarity if the bases are parallel. So you don't actually have to go through that every time if it takes too long. So this is L. Now, again, similar triangles. the ratio of the heights is the same as the ratio of the sides. Similarity preserves everything on the inside as well, not just on the outside. So, as you can see here, the triangle, the bottom triangle, is 3 times bigger. The side is 3 times bigger, and that means the height should be 3 times bigger as well. The height will be 3L. And now we can do something very similar, right? L, 3L, because 1 to 3 ratio of sides, so 1 to 3 ratio of heights. And now we would have that L plus 3L, this distance over here, equals 2y. Or 4L equals 2y. Y is just 2L. 2L, 2L. Or, no, let's not do that, actually. Now let's say that L is y over 2. We're trying to find everything in terms of x and y. So this height over here is nothing but y over 2. And let's cross this out for now. Over here, it's going to just be y, because 2 times y over 2. And now the area over here is half times x times y over 2, as you can see here. And that's the area of this green region. So the area of this region over here is just the area of the triangle, which we found to be 3xy by half base height formula, minus the area of the blue region, and the green region. And this is just, we can move this out of the way. We're done with that for now. Oops, let's get that far away. Move it there. And now the area of the blue region is half xy. And the green region was 1/4 xy, right? 1/2 times y over 2 is y over 4, and then y over 4 times x is xy over 4. And then this becomes, if we find a common denominator, minus 2xy over 4 minus xy over 4, which is 9xy over 4. And this is equal to 21. Remember, we've given the area of table is 21. Now we found the area of table in 2 ways, in terms of variables and numerically given in the problem. So 9xy by 4 is 21. Uh-oh, 2 variables, 1 equation. Don't worry. The thing is, we're not solving an equation here. Remember, we're just trying to find the area of trig, which is 6xy. And we know 9xy over 4 is 21. So all we have to do is solve for xy. So xy is 4/9 times 21, right? By just multiplying by 4/9 to both sides, which is just going to be 4/3 times 7, 28 over 3. So 6xy is 6 times 28 over 3, which is just 56. And that's going to be our answer. So let's quickly review. The key ideas for this problem was to realize that table, well, we first assigned variables to make things to rewrite the condition. And then we saw the area of the rectangle, 6xy. Now what is the area of table? Well, the area of table is just the area of this triangle, which is 3xy minus the blue regions and the green regions. How do we find the area of those regions? Well, we knew the base in terms of x's and y's, and then we found the height using similar triangles, and seeing that the heights of both of these triangles combined form 3x, and we did something similar here, right? These 2 heights combined form 2y. And then after that, we just found the areas of both of these regions, plugged them in, and found our answer, or not our answer. We found that 9xy over 4 is 21, solved for xy, and then found the area of the rectangle, which is 6xy. A clever problem, but now we're ready to move on to lengths of complex shapes. And we've got some interesting problems where we'll be not finding area this time, but now breaking up lengths and doing some cool manipulation. You can click on the next video, it's going to be right over there. Hope you enjoyed. If you enjoyed this video, also be sure to subscribe.